Alex Pentland, a member of the advisory board. I wish I could be there in person, but unfortunately that didn't work out. So we're going to do this virtually, and hopefully that will be almost as good, but I get to miss the conversations and the feedback. So hopefully we'll do that another time. So I'm going to talk about technology for trustworthy AI. And I have three topics I want to cover in 20 minutes. One is human AI systems, because of course the humans in the system are just as important as the AI. They don't operate independently, and a marriage between the two is critical. The second is a thing called causal filtering. We know that causal investing, causal processes are important, but which processes, which connections? And this is a way of looking through millions and millions of potential connections and determining which ones might be causal. And the final is secure AI, so cryptographic methods for secure inference, for auditing, and so forth. So the first is human AI systems. It's worth giving a short history of how we've screwed up in the past so that we don't do it again. In the early 60s, you had early types of AI, which were essentially linear solvers with constraints or logic, sort of very formal sort of methods. And famously, the Soviets tried to have a planned economy based on this, which didn't work out so well, because you need really accurate models, and the economy is just too complicated. Nonetheless, this type of technology is everywhere. It's in your Excel spreadsheets, in planning, in logistics. It is ubiquitous in areas where the models are really good. In reaction to this, a generation later, we had expert systems. The idea was, well, exact models may be difficult, but there are heuristics that experts have, and we can use those. The trouble is that it's really tempting to use the same heuristic everywhere. And you see this in enterprise systems, in management systems everywhere, where the same rules apply everywhere, but of course, everywhere isn't the same. All the different markets aren't the same. So in fact, what you get is suboptimal performance because you're applying a uniform rule. Nonetheless, these are everywhere, again. Not big, it's not managing the entire sort of world, but it manages most of the sort of siloed systems that we have. The next one was crowdsourced behaviors, which have the unfortunate characteristic of winner take all. The early people who got a lot of data were able to leverage that in an exponential way to dominate markets everywhere. Europeans call them hyperscalers. And they're now so dominant that the large hyperscalers are larger than the economies of major countries. And that seems problematic, potentially. And so, again, though, this is everywhere. Everything uses the data that from behavior to be able to market, to be able to optimize, and generally produces good results, except for this concentration of power. And now we have the new large language models and new wave of sort of AI, and the question is what's going to happen. One of the faults of how it's used is, and it's not a fault of the technology, it's a fault of how people use it, is they assume that the answers that come from these AI are things that can be trusted in some way. So they say, well, let's just estimate what's going on and then we'll do it. But of course, people don't do that. What people do is they're influenced by what other people do. And so if you're going to interface with people and you're going to put AIs in there, one natural way to sort of think about it is that the AI is just one of your social network and giving you some advice, and you should take it as like a prior probability. And you see this in weather reports and climate change models and so forth, where there are many, many models which differ from each other, and people look at that and then make decisions. In fact, this sort of model as a prior works out quite well in many different situations. So for instance, in a meta study recently of 300 AI systems, what they found was that systems that tried to actually find answers and use those directly generally performed worse than just humans or just expert systems. On the other hand, open problems, where you're trying to sort of figure out what's going on, that's abductive reasoning rather than deductive, the human AI teams were very surprisingly almost always better. So what does that look like? Um, so what it looks like is this in investing. What you see is quantitative people just looking at the numbers, making trades, and they do quite well. But if you also take into account what the street believes, you can reduce your risk with only slight reduction in your accuracy of predictions. And in fact, the Sharpe ratio of the guys down here who take into account what the street is saying, the social context, um, are better in the long-term repeated trials than the people who are pure quantitative generally. Um, so that's the first topic is that don't trust this stuff to be the answer. Trust it as a way of suggesting possibilities, of shaping the thing that you construct as your strategy. So that's thing one. Uh, Thing two is this causal filter. Well, what features do you pay attention to when you're building your models and when you're doing things? Well, we know about some, but there are probably other ones that we're not familiar with. Situation changes and so forth. And in fact, financial data is very complicated, and all sorts of other things might uh, affect it. So, shipping patterns, weather patterns, all sorts of things. Which of these are the features you want to incorporate? And do you want to incorporate all of them? All of them is difficult because there's a huge number of factors you might have. And as you get fewer observations, of course, you're less certain about what's going on. Um, and so the way I've developed to be able to think about this is you think about all these sort of agents, all these entities that are acting in the world, and particularly people acting, um, are parts of systems. And you can observe some of the systems, but not all of the systems. But the thing that is interesting is if you look at the probability structure for people making actions, for instance, investing in things, sending messages, other sorts of actions, it's highly correlated with the systems that they're part of. So if they're part of a functional group, that group will become occasionally active as some opportunity comes up, and the people who are interacting with that group will then also act. So we know that individuals and organizations are bursty, long tail sort of behaviors. And what happens is that the pauses between behaviors, between actions, are correlated over the long term. If these people are actually working with each other, in other words, if there's a potentially causal relationship. And we've been able to do things that are really pretty surprising. So, for instance, looking at Ethereum, we've been able to, with really quite decent accuracy, determine the identities, these are all synonymous identities, but the identities that a single person has in their actions. So this becomes particularly critical when you're looking at, for instance, bot farms or fraud or things like that. And what's correlated there is the length of the silences between their actions. And you see we got a precision of 0.75 with a really good recall. Um, and you can actually improve this by using some of the graph techniques. Similarly, you can ask, well, which actors that you see, which synonymous identities are part of a group? And it turns out that this correlation in silence times predicts how tightly the organization is organized, and you get to have a much better sense of who's members and who's not. Again, money laundering, state actors, financial actors that are trying to hide their identity can be pulled out in this way. And this is again from encrypted data. So we've been able to use this in a variety of ways. This is just one example. One is identifying apparently random people who are in fact state actors and troll farms and things like that, because their actions have correlated silences between them. You know, if something happens, they all light up and talk about something. And it's not a matter of content. We don't look at the content, it's all encrypted. And we can do this between platforms like Telegraph, which is fully encrypted, and Signal, which is fully encrypted. We can do it between Twitter and Telegraph. It's pretty interesting. And what you're doing is you're pulling out things that are highly predictive of each other, which doesn't prove causality, but winnows down those trillions of possibilities to a relatively small number that then you can test with more expensive methods. Final thing I want to talk about is secure AI. So when you use AI, people can see your queries, maybe the data isn't protected. How do you actually put things together so that you have systems that can't be spied on, can't be easily corrupted? And particularly this is difficult if these are geographically distributed systems. And so we've developed a whole series of methods to do this, and really cutting edge cryptography. I'll show you the website where you can see it later. And the idea is that today, the way the world is organized, you have suppliers, customers, other work groups, your work group, and the sharing permissions between them are very different. There's proprietary data, there's personal data. And what you have to have is you have to have AI and inference that respects these boundaries. This is particularly important in service industries. And so this forces you to a decentralized structure. If you have everything in one place, then that's a single point of failure. It's a single point where you can sort of break in and get things. If it's decentralized, then they might break in and catch one or two things, but they can't catch the whole thing. And it actually becomes much easier to defend. So you say, well, but if the data is never put together, how do you make inferences? Well, we've developed a series of methods for doing this. You've all heard of probably federated learning. We've developed sort of simple socio-technical things that use legal systems and digital attestations. For instance, in the United States, we worked with Fidelity to deploy this, a thing called Akoya, that very quickly captured 90% of all the bank accounts in the United States. And what it was a way of banks attesting to the know your customer clearance of their customer, but to another bank. So that means you don't have to do know your customer for every single thing. You can attest to bank account levels without sharing the exact level, and so on and so forth. And we're now doing this in health systems. We've talked about this earlier, and happy to go into it more. So some of the methods that are used for more sophisticated versions of this are secret sharing or multi-party computations, secure multi-party. And this is just a graphic of it. It's a way of putting together data that is provably secure and can be actually Turing complete, so you can compute anything. And now you're having versions of this which are really quite efficient. And you can even do this with things that are quantum proof, which is interesting and different than, for instance, homomorphic. Another thing that's particularly interesting is finding relevant data. So there are simple things like private set intersection, where you encode the data, you encrypt the data in a way that preserves the relative ranking of certain things. You can think of it as a junior version of homomorphic encryption if you want, but it's technically it's private set intersection. What this lets you do is identify when data sets have elements that are similar to each other in the same sort of context. And there are now sophisticated versions that we're working with other organizations that let you actually estimate the value of the data to other people. And that gives you the ground for building data markets where you have some reasonable idea about the value of a new data set before you share the data. Very important, particularly in sort of financial things. Another element that is important in secure systems is zero knowledge proofs. And we just had a paper out on this where what you can do is you can have attestations that the inferences you're getting are using the model and the data that you think they are, and it wasn't that somebody poisoned it or swapped it out. So take a look at that. Again, this can be done actually quite cheaply after an initial expense of computing the right sort of hashes. So another way to sort of think about making this secure. And if you want to know more about it, you can look at transformers.mit.edu. It has code, it has papers, it has both the legal and the cryptography, and some of the things about data provenance that you probably need to know also. So let me just stop there. And hopefully this is interest to you and useful, and happy to answer questions, but I guess not now because this is a pre-recorded. Thank you and hope to see you all soon.